Hello, in this lecture we'll find out the radius of a circle. In the drawing we have quadrilateral ABCD. Inside this quadrilateral we have this circle. We know that side AB equals to 2 units in its length, side BC equals to 8 units, side DC also equals to 8 units. In addition, this is angle ABC that is equals to 90 degrees, and this is also angle DCB. This is also equals to 90 degrees. In its size, it is a right angle. Again, our mission is to find out the radius, the area of this circle. Okay, so in order to find out the area of this circle, we'll do a construction. That is to say, we'll extend side DA and side CB of this quadrilateral by a straight line until they touch each other. So this is the touching point. We define the touching point as M. By doing this construction, we create here the right big triangle, triangle MDC. We focus on this right big triangle, triangle MDC. And we define this angle as theta. So in this right big triangle MDC, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Why? Because (90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Okay. So here we have BC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. Then we extended the straight line BC by a straight line, and the result is CM. When you extend a straight line by a straight line, the result must be also a straight line. So CM is a straight line. If you focus on the upper side of the straight line CM at point B, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is a right angle, it is equal to 90 degrees, plus the missing angle that is actually angle ABM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of the straight line CM at point B to 180 degrees, the missing angle must be equal to 90 degrees. So in the next step, we will focus on the right small triangle ABM. On the right small triangle MBM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. In the next step, we'll prove that the right big triangle DCM is similar to the right small triangle MBA. Okay, so I write it down. We'll prove that the right big triangle DCM is similar to this right small triangle MBA. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Actually, this is angle DCM on the big right triangle DCM, and it is equals to this angle that is actually angle ABM in the right small triangle MBA. Repeat again. Angle DCM in the right big triangle DCM equals to angle ABM in the right small triangle MBA. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. It is a common angle that belongs to both triangles. So we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the big right triangle DCM, we will call to angle theta angle DMC, and it equals to itself. If we relate to angle theta as it belongs to the small right triangle MBA, it will be called as angle AMB. Repeat again. This equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So I write it down. This is angle MDC in the big right triangle DCM, and it is equals to this angle that is actually angle MAB in the small right triangle MBA. Repeat again. Angle MDC in the big right triangle DCM equals to angle MAB in the small right triangle MBA, They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles of the right big triangle DCM are correspondingly equal to all the three angles of the right small triangle MBA. Therefore, we actually proved that those two right triangles, they are similar to each other according to angle similarity rule. So I write it down. The big right triangle DCM is similar, this is the sign of similar, to the right small triangle MBA according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side DC in the big right triangle DCM over side AB in the small right triangle MBA equals to side CM in the big right triangle DCM over side BM in the small right triangle MBA. Repeat again, we derive that DC over AB equals to AM over BM. DC equals to 8 units in length over AB. AB equals to 2 units in length, and it is equals to CM. CM, from the drawing it is very easy to see that CM equals to CB plus BM. That is to say CM equals to CB, that is 8 plus BM. So in total CM equals to 8 plus BM. So we substitute CM here in this equation by 8 plus BM, and we have to divide it by BM. In Coulomb found out that 8 over 2 equals to 8 plus BM over BM. 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here we multiply this equation by BM, and we get that 4 times BM equals to 8 plus BM. Here we subtract BM from this equation, and we get that 4BM minus BM is 3BM, so 3BM equals to 8. Here we divide this equation by 3, and finally we get that BM equals to 8 over 3 units in its length. So this line 7 BM equals to 8 over 3 units in its length. In the next step, we'll focus on the right small triangle MBA, and we'll implement the Pythagoras theorem on this right small triangle MBA. Here by PT is a progression for Pythagoras theorem. In this small right triangle MBA, according to the Pythagoras theorem, AM square, that is the square of the hypotenuse, must be equal to AB square plus BM square. Okay, again, according to the Pythagoras theorem, in the right triangle MBA, AM square equals to AB square plus BM square. So AM square, that is the square of the hypotenuse, equals to AB square. AB is 2, therefore AB square is 2 square, that is 4, plus BM square. BM is 8 over 3, therefore BM square is 8 over 3 square, that is 64 over 9. So we can find out that AM square equals to 4 plus 64 over 9. So AM square equals to, here we multiply 4 by 9 and then we divide it by 9 in order to have a common factor with 64 over 9. So 9 times 4 is 36. So in total, in the numerator of this expression, we will have 36 plus 64 divided by 9. 36 plus 64 is 100, and we have to divide it by 9. If we found out that AM square equals to 100 over 9. Here we'll take a root out of this equation, and we get that AM equals to the square root of 100 over 9. The square root of 100 over 9 equals to the square root of 100, that is 10, over the square root of 9, that is 3. So we have found out that AM, the hypotenuse AM equals to 8 over 3 units in its length. Here AM, the hypotenuse AM here equals to 8 over 3 units, 10 over 3 units in its length. AM equals to 10 over 3 units in its length. In the next step, we'll do another construction. That is to say, we'll draw perpendicular on side BC in such a way that the perpendicular will be also tangent to the circle. Okay? It is absolutely possible to do it. So first of all, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular inside BC is T. We define the point of tangency of the perpendicular with this circle as K. In the next step, we'll extend this perpendicular KT by straight line until it touches side AD. And we will define the touching point of the extended perpendicular KT with side AD as point L. By doing this construction, we created the right big triangle, triangle MLT. this big right triangle, triangle MLT, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. Okay. In the next step, we define the center of this circle, this point as O. We define the point of tendency of this tangent AB with this circle as N. And finally, we define the point of tendency of this tangent, tangent BT, with this circle as H. We will define the radius of this circle as X. So point O is the center of the circle, point H is the point of the circle itself, therefore OH is the radius of this circle. According to our definition, the radius of this circle is X, so OH equals to X. This is the radius of the circle, is equal to X according to our definition. Here we can implement rule 1. I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have a circle and we have tangent AB. This is tangent AB. That is tangent to this circle at point M. Point M is the point of tendency. And we have the radius OM that is drawn to point M. That is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. You can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OH, this is radius OH, that is drawn to point H, that is the point of tendency of tangent BT with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius HO. If BT is perpendicular to HO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. This is according to rule 1. Likewise, we join points O and N together by straight line. Line segment ON is the radius of this circle that is equal to X. Only to our definition. Again, we have the radius ON that is drawn to point N. Therefore, according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. Likewise, we join points O and K together by straight line. OK, line segment OK is the radius of this circle that is equal to X. Again, we have the radius OK that is drawn to point K. Therefore, according to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees in its side. In the next step, we focus on this small quadrilateral OKTH. In this small quadrilateral OKTH, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of the fourth angle. In total, they must be equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, the missing angle here must be equal to 90 degrees. So inside quadrilateral OKHT, we have 4 right angles. Therefore, we can relate to this quadrilateral OKHT as a rectangle. We also know that the opposite sides of a rectangle are equal to each other. So side OK must be equal to side HT in rectangle OKHT. But OK is x, therefore HT must be also equal to x. Likewise, according to the sum rule, OH must be equal to KT, but OH is x, therefore KT must be also equal to x. So actually, we found out that quadrilateral OKHT is not a rectangle but a square because all of its sides are equal to each other. We repeat on the same process on this quadrilateral ONBH. On quadrilateral ONBH, we have 1, 2, 3 rectangles, therefore the fourth angle must be also equal to 90 degrees, according to the sum rule. So quadrilateral ONBH has 4 rectangles, therefore quadrilateral ONBH, we can relate to it as a rectangle, and you know that the opposite sides of a rectangle are equal to each other, that is to say ON equals to HB. But ON is x, therefore HB must be also equal to x. According to the sum rule, OH must be equal to NB. But OH is x, therefore NB must be also equal to x units in its length. So we found out that quadrilateral ONBH is not a rectangle but a square. In conclusion, we found out that BT equals to x plus x, that is 2x. BT equals to 2x, so we can write here the line segment BT equals to 2x units in its length. In the next step, we'll prove that the right big triangle LTM is similar to the right small triangle MBA. So I'm writing down the right big triangle LTM is similar to the right small triangle, this right small triangle MBA. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this is actually angle LTM. This is angle LTM. In the big right triangle LTM, and it is equal to this angle, that is actually angle ABM. Angle ABM in the small right triangle MBA. Repeat again. Angle LTM equals to angle ABM. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. So we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to angle theta as it belongs to the big right triangle LTM, we will call to angle theta as angle LMT. And it equals to itself. So if we relate to angle theta as it belongs to the small right triangle MBA, it will be called angle AMB. So actually this equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So this is actually angle MLT in the big right triangle LTM, and it is equals to this angle, that is actually angle BAM in the small right triangle MBA. Repeat again. Angle MLT in the big right triangle LTM equals to angle BAM in the small right triangle MBA. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in the big right triangle LTM are correspondingly equal to all the three angles in the small right triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The big right triangle LTM is similar. This is the sign of similar to the small right triangle MBA according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side LT in the big right triangle LTM over side AB in the small right triangle MBA equals to side TM in the big right triangle LTM over side BM in the small right triangle MBA and it is also equals to side LM, that is the hypotenuse of the big right triangle LTM, side LM over side AM, that is the hypotenuse in the right small triangle MBA. Repeat again. We found out actually that LT over AB equals to TM over BM equals to LM over AM. LT is the missing side, so we leave it as it is. Over AB, AB is 2, so we substitute AB by 2. And it is equals to TM. From the drawing, it is very easy to see that Tm in total equals to Tb plus Bm. That is to say, Tm equals to Tb, that is 2x, plus Bm, that is 8 over 3. So in total, Tm equals to 2x plus 8 over 3. We substitute Tm here by 2x plus 8 over 3 divided by Bm. Bm equals to 8 over 3. And Bm equals to 8 over 3, so we substitute Bm by 8 over 3. Divided by Lm. The hypotenuse Lm of the big right triangle LTM, in total it is equals to La plus Am. So it is La, that is the missing side, so we leave it as it is, plus Am, that is 10 over 3. So in total Lm equals to La plus 10 over 3. So we substitute Lm by La plus 10 over 3 divided by AM. The hypotenuse AM of the small right triangle MBM equals to 10 over 3 units in its length. So we substitute AM in this equation by 10 over 3. Okay. So we have here a long equation. Those two sides in this long equation, they are equal to each other. Therefore we create the first equation from those two sides that are equal to each other. So according to the first equation, LT over 2 equals to 2x plus 8 over 3 over 8 over 3. So LT over 2 equals to, we have 2x plus 8 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to have a common factor with 8 over 3. And we will get that 2x times 3 is 6x. So in total, in the numerator of this expression, we will have 6x plus 8 divided by 3, and also it is divided by 8 over 3. We'll focus on this side of the equation. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. So we cancel 3, we're left only with LT over 2, that is equal to 6x plus 8 over 8. So here we cross multiply this equation and we get that 8 times LT equals to 2 times 6x plus 8. Here we divide this equation by 2 and we get that 8 over 2 is 4, so in total in this side of the equation we have 4LT. That is equal, in the other side of the equation we have 2 over 2 is 1, so we left only with 6x plus 8. Here we divide this equation by 4, and finally we'll get that LT equals to 6x over 4 is 1.5x plus 8 over 4 is 2. So in total we found out that the length of line segment LT is 1.5x plus 2. So we can write down in the original drawing that this line segment LT is equals to 1.5x plus 2. We'll continue to focus on this long equation. Those two sides, they are equal to each other, so we'll create equation 2 from those two sides that are equal to each other. So according to equation 2, we get that 2x plus 8 over 3 over 8 over 3 equals to 10 over 3 plus LA over 10 over 3. So in this side of the equation we have 2x plus 8 over 3. We multiply 2x by 3 and then we divide it by 3 in order to work our factor with 8 over 3. 2x times 3 is 6x. So in total in the numerator of this expression we have 6x plus 8 divided by 3. And we have to divide it also by 8 over 3. And it is actually equals to, here we have 10 over 3 plus LA. Here we'll multiply LA by 3 and then we divide it by 3 in order to have a common factor with 10 over 3. And we get that LA times 3 is 3LA. So in total in the numerator of this expression we have 3LA plus 10 divided by 3, and also we have to divide it by 10 over 3. So in this side of the equation we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. In the other side of the equation, we have here 3 in the numerator and 3 in the denominator. So 3 also will get cancelled. After we cancel 3 on both sides of the equation, we left only in this side of the equation, we have 6x plus 8 over 8. That is equal to, in the other side of the equation, we have 3LA plus 10 over 10. So here we'll cross multiply this equation and we'll get that 10 times 6x plus 8 equals to 8 times 3LA plus 10. So repeat again. We actually found out that 10 times 6x plus 8 equals to 8 times 3LA plus 10. Here we'll divide this equation by 2 and we'll get that 10 over 2 is 5, so in total this of the equation we have 5. Inside the brackets we have 6x plus 8 equals to 8 over 2 is 4. So in total, in this side of the equation we have 4. Inside the brackets we have 3LA plus 10. So here we'll open the brackets on both sides of this equation and we get that 5 times 6x is 30x plus 5 times 8 is 40. That is equals to 4 times 3LA is 12LA plus 4 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled. After we cancel 40, we left only with 30x. That is equals to 12LA. Here we divide this equation by 12. And finally we'll get that LA equals to 30x over 12, that is 2.5x. Okay, so actually found out that this line segment LA or AL equals to 2.5x in its length. In the next step, I will copy this small quadrilateral ALBT in a new page with the circle that is inscribed inside it. And we will analyze this small quadrilateral ALBT. So actually, this is the small quadrilateral ALBT with the circle that is described inside it, with the copy from the original drawing. Here we define the point of tendency of tangent AL with this circle as K. We define the point of tendency of tangent AB with this circle as N. We define the point of tendency of tangent BT with this circle as G. And finally, we define the point of tendency of tangent NT with this circle as H. Here we can implement all two. I'll repeat again quickly on all two. According to all two, the lengths of two tangents from a common standpoint to a circle are equal. In the drawing we have a circle and we have the common standpoint point P. From the common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to all two they are equal to each other. That is to say PA equals to PB. We can actually implement all two in our drawing. Why? Because in our drawing, if we focus on the common standpoint point A, from the common standpoint A, we have two tangents to this circle, tangent AN and tangent AK, and according to all two, they are equal to each other. That is to say, AN equals to AK. AN equals to AK, according to all two. Repeat again. Tangent AN equals to tangent AK according to all two. So if we define the length of tangent AN as A, then the length of tangent AK must be also equal to A because they are equal to each other. So in conclusion, we found out that AN equals to AK equals to A. In the next step, we'll focus on the common standpoint point B. From the common standpoint point B, we have two tangents to this circle, tangent BN and tangent BD, and according to all two they are equal to each other. That is to say, BN equals to BG. I'll repeat again. According to the sum rule, all two, if we focus on the common standpoint point B, tangent BN must be equal to tangent BG. So if we define the length of tangent BN as B, then the length of this tangent BG must be also equal to B because they are equal to each other. In conclusion, we found out that BN equals to BG equals to B. In the next step, we'll focus on the common standpoint point T. So from the common standpoint point T, we have two tangents to this circle, tangent TH and tangent TG. And according to all two, they are equal to each other. So that is to say TH equals to TG. Repeat again. The common standpoint point T, tangent TH must be equal to tangent TG according to the sum all two. So actually, if we define the length of tangent TG as C, then the length of tangent TH must be also equal to C because they are equal to each other. And finally, we focus on the common external point, point L. On the common external point, point L, we have two tangents to this circle, tangent LK and tangent LH, and according to rule 2, they are equal to each other. This is to say, LK equals to LH, according to the same rule, rule 2. Repeat again. The common external point, point L, tangent LK must be equal to tangent LH according to rule 2. So if we define the length of this tangent LH as D, then the length of tangent LK must be also equal to D because they are equal to each other. Okay, so in conclusion, we found out that at the common external point, point L, tangent LK equals to tangent LH equals to D. In the next step, we join side LA to side BT, side AL to side BT. From the domain, it is very easy to see that AL plus BT in total it is equals to A plus B plus C plus D. So AL plus BT in total equals to A plus B plus C plus D. Likewise, we join side AB to side LT. So it is AB plus LT. AB equals to A plus B and LT equals to C plus D. So in total, AB plus LT equals to A plus B plus C plus D. So we found out that those two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. So we can write down that AL plus BT equals to AB plus LT. Okay. So we have AL. AL equals to 2.5x. Therefore, we substitute AL in this equation by 2.5x plus BT. From the domain, it is very easy to see that BT equals to x plus x, that is 2x. So we substitute BT by 2x in this equation, and it is equals to AB. AB equals to 2, so we substitute AB in this equation by 2 plus LT. Here LT, this line segment LT equals to 1.5x plus 2, so we substitute LT in this equation by 2 plus 1.5x. So in conclusion, we found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x. That is equals to 2 plus 2, that is 4, plus 1.5x. So in conclusion, we found out that 4.5x is equals to 4 plus 1.5x. Here we subtract 1.5x from this equation, And we get that 4.5x minus 1.5x is 3x. Is equal to 4. Here we divide this equation by 3, and finally we get that x equals to 4 over 3 units in its length. So, actually found out that the radius x of this circle equals to 4 over 3 units in its length. X equals to 4 over 3 units is the radius of the circle. Our mission is to find out the area of this circle. We know that the area of any circle is equals to pi times the radius squared. In our specific circle, the area will be equal to pi and the radius is x, so the radius square is x squared. So the area of our circle is pi x squared. X is 4 over 3, so we substitute x is pi 4 over 3, so it is pi. If x is 4 over 3, it means that x squared is 4 over 3 squared. So the area of our circle equals to pi times 4 over 3 squared. So it is pi times 4 over 3 squared. 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of our circle, that is the area that we are looking for in this equation, equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. And that is the answer to our question. Repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equals to 5.585 square units. In the next step, I will summarize the lecture. In this lecture, we found out the area of this circle. In the domain, we have quadrilateral ABCD. Inside this quadrilateral, we have this circle. In addition, we know that side AB of quadrilateral ABC equals to 2 units in its length, side BC equals to 8 units in its length, and side DC also equals to 8 units in its length. In addition, we know that this is angle ABC that is equals to 90 degrees in its size, and this is also angle DCB, also it is a right angle that is equals to 90 degrees in its size. Our mission is to find out the area of this circle. In order to find out the area of this circle, we did a construction, that is to say, we extended side DA and side CB of this quadrilateral by a straight line until they touch each other. They touch each other at this point. We defined their touching point as point M. By doing this construction, we created here the right big triangle, triangle DCM. In the right big triangle, triangle DCM, we defined this angle as theta. We continue to focus on the right big triangle, triangle DCM. This big right triangle DCM, this angle equals to theta according to our definition. This angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees. And 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. CB is one side of quadrilateral ABCD, therefore it is absolutely a straight line. Then we extended the straight line CB by straight line. The result is CM. When you extend the straight line by straight line, the result must be a straight line. So the result CM must be a straight line. We know that CM is a straight line. So if you focus on the upper side of this straight line CM at point B, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of CM at point B? We have this angle that is equal to 90 degrees plus the missing angle that is actually angle ABM. In total, the sum of those two angles must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles on the upper side of CM at point B to 180 degrees, the missing angle must be equal to 90 degrees. Then we focus on this small right triangle MBA. In this small right triangle MBA, this angle equals to theta. This angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus theta. Okay, in the next step, we proved that the big right triangle DCM is similar to the small right triangle MBA. Why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta. That is a common angle, it belongs to both triangles. So we can write out that angle theta equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles of the right big triangle DCM are correspondingly equal to all the three angles of the right small triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side DC in the big right triangle DCM over side AB in the small right triangle MBA is equal to side CM in the big right triangle DCM over side BM in the small right triangle MBA. Repeat again, we will derive that DC over AB equals to CM over BM. DC is 8, AB is 2. CM, what is the length of CM? From the drawing, it is very easy to see that CM in total it is equal to CB plus BM. That is to say, CM equals to CB, that is 8, plus BM, that is actually the missing side. So in total, CM equals to 8 over BM. So here CM equals to 8 plus BM. CM equals to 8 plus BM. And we have to divide it by BM. So in conclusion, found out that 8 over 2 equals to 8 plus BM over BM. 8 over 2 is 4, so 4 equals to 8 plus BM over BM. Here we multiply this equation by BM and found out that 4 times BM equals to 8 plus BM. Here we subtracted BM from this equation and found out that 4BM minus BM is 3BM, so 3BM equals to 8. Here we divided this equation by 3, and finally found out that BM equals to 8 over 3 in its length. Here, this line segment BM equals to 8 over 3 units in its length. Then we focus on this right small triangle ABM. Implemented the Pythagoras theorem on this small right triangle MBA. This small right triangle MBA, AM square equals to, according to the Pythagoras theorem, AM square equals to AB square plus BM square. Repeat again, the small right triangle MBA, AM square equals to AB square plus BM square. So AM squared, that is the square of the hypotenuse, equals to AB square. AB is 2, therefore AB square is 2 squared, that is 4, plus BM square. BM is 8 over 3, therefore BM square is 8 over 3 squared, that is 64 over 9. So we found out that AM square equals to 4 plus 64 over 9. AM square equals to, here we multiply 4 by 9, and then we divide it by 9 in order to work on factor with 64 over 9. 9 times 4 is 36, so in total in the numerator of this expression we have 36 plus 64 divided by 9. 36 plus 64 it is 100, and we have to divide it by 9. So in conclusion, found out that AM square equals to 100 over 9. We took out of this equation and finally found out that AM equals to the square root of 100 over 9. the square root of 100 over 9 equals to the square root of 100, that is 10, over the square root of 9, that is 3. So in conclusion, we found out that the hypotenuse AM equals to 10 over 3 units in its length. Here the hypotenuse AM of the right triangle BA equals to 8 over 3 units in its length. In the next step, we did another construction, that is to say, we drew perpendicular on side BC in such a way that the perpendicular on BC will be also tangent to this circle. Okay? So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular and side BC as T, and we define the point of tendency of this perpendicular with this circle as K. Then we extended the perpendicular TK by straight line until it touches side DA, this point. We define the touching point of the extended perpendicular TK with side DA as L. By doing this construction, we created the right big triangle LTM. In the right big triangle LTM, this angle equals to theta, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus theta. In the next step, we define the center of this circle here, this point is O, and we defined the point of tendency of tangent AB with this circle as N, and finally we define the point of tendency of tangent BT with this circle as H. Then we join points, we define the center, the radius of this circle as X. Then we join points O and H together by straight line. Point O is the center of the circle, point H is the point of the circle itself, therefore OH is the radius of this circle, and according to our definition, the radius of this circle is X. Therefore OH equals to X. We have a rule 1, the radius OH is drawn to point H, that is the point of tendency of tangent BT with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BT will be perpendicular to the radius HO. If BT is perpendicular to HO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. Then we joined points O and N together by straight line. ON is the radius of this circle that is equal to X. The radius ON is drawn to point N, therefore this angle equals to 90 degrees, this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and K together by straight line. Line segment OK is the radius of this circle that is equal to X. The radius OK is drawn to point K, therefore according to rule 1, this angle equals to 90 degrees and this angle equals to 90 degrees. Then we focus on this quadrilateral OKHT. This small quadrilateral OKHT, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral OKHT we have 4 right angles, therefore we can relate to this quadrilateral OKHT as a rectangle. And we know that the opposite sides of a rectangle are equal to each other, that is to say, side OK equals to side HT. But OK is X, therefore HT must be also equal to X. Likewise, according to the sum rule, side OH must be equal to side KT, but OH equals to X, therefore KT must be also equal to X. So actually found out that quadrilateral OKHT is not a rectangle but a square, because of the fact that all of its sides are equal to each other. Likewise, we repeated on the same process in this small quadrilateral NOBH. Inside this small quadrilateral we have 1, 2, 3 rectangles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral BH and O we have 4 rectangles, therefore we can relate to this quadrilateral as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, NO must be equal to BH in rectangle NOBH. But NO is X, therefore BH must be also equal to X. Likewise, according to the same rule, side OH must be equal to the opposite side NB in rectangle NOBH. But OH equals to X, therefore NB must be also equal to X. So actually found out that quadrilateral NOBH is not a rectangle but a square. In conclusion, found out that BT in total equals to X plus X, that is 2X. Here BT equals to 2X. Here BT equals to 2X units in its length. Then we proved that the big right triangle LTM is similar to the small right triangle, MBA. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, it is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus theta, therefore they are equal to each other. So we have proved that all the three angles of the right big triangle NTM are correspondingly equal to all the three angles of the small right triangle MBA. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that LT over AB equals to TM over BM equals to LM over AM. LT is the missing side, so we leave it as it is. AB is 2, and it is equals to TM over BM. What is the value of TM? Here, TM, from the domain, it is very easy to see that TM in total equals to TB plus BM. That is to say, TM equals to TB, that is 2x, plus BM, that is 8 over 3. So in total, TM equals to 2x plus 8 over 3. Here, Tm equals to 2x plus 8 over 3 over Bm. Bm equals to 8 over 3. Here, Bm equals to 8 over 3, and it is equals to Lm. What is the value of Lm? Here, Lm, in total, Lm equals to La plus Am. That is to say, Lm equals to La, that is the missing side, plus Am, that is 10 over 3. So in total, Lm equals to La plus 10 over 3. Here, Lm equals to La plus 10 over 3 over Am. Am equals to 10 over 3. Here, Am equals to 10 over 3. So here we created this long equation. We created the first equation from those two sides that are equal to each other. So according to the first equation, LT over 2 equals to 2x plus 8 over 3 over 8 over 3. Okay? So in this equation we have 2x plus 8 over 3. Here we multiply 2x by 3 and then we divide it by 3 in order to overcome factor with 8 over 3. And found out that in total in the numerator of this expression we have 2x times 3 is 6x. So in total in the numerator of this expression we have 6x plus 8. 6x plus 8 divided by 3, and we have to divide it also by 8 over 3. So in conclusion, found out that LT over 2 equals to 6x plus 8 over 3 over 8 over 3. Here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancel 3, we left only with LT over 2, that is equal to 6x plus 8 over 8. Here we cross multiply this equation and found out that 8 times LT equals to 2 times 6x plus 8. Here we divided this equation by 2 and finally found out that 8 over 2 is 4, so in total in this side of the equation we have 4LT, that equals to 2 over 2 is 1, so we left in this side of the equation only with 6x plus 8. So in conclusion found out that 4 times LT equals to 6x plus 8. Here we divided this equation by 4 and finally found out that LT equals to 6x over 4, that is 1.5x, plus 8 over 4, that is 2. So in conclusion found out that LT, the length of line segment LT is 1.5x plus 2. Here, this line segment LT equals to 1.5x plus 2. Here we have those two sides of this long equation, they are equal to each other, so we get the equation 2 from those two sides that are equal to each other. So according to the second equation, 2x plus 8 over 3 over 8 over 3 equals to LA plus 10 over 3 plus over 10 over 3. Okay, this is the equation. So in this side of the equation we have 2x plus 8 over 3. Here we multiply 2x by 3, then we divide it by 3 in order to overcome factor with 8 over 3. So in total in the numerator of this expression we have 2x times 3, that is 6x. So in the numerator we have 6x plus 8 divided by 3, and then we have to divide it by 8 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. In the other side of the equation we have here 8 over 3 plus LA. Here we multiplied LA by 3, then we divided by 3 in order to make a common factor with 8 over 3. So in total, in the numerator of this expression we have 3 times LA plus 10 divided by 3, and then we have to divide it by 10 over 3. So here we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancel 3 on both sides of the equation, we left only with 6x plus 8 over 8. This equals to 3LA plus 10 over 10. Here we cross multiply this equation and found out actually that 10 times 6x plus 8 equals to 8 times 3LA plus 10. Here we open the brackets on both sides of the equation and found out that actually we divided this equation by 2 and found out that 10 over 2 is 5, so in this side of the equation in total we have 5 times 6x plus 8. 8 over 2 is 4, so in total in this side of the equation we have 4. Inside the brackets we have 3LA plus 10. Here we open the brackets on both sides of the equation and we found out that 5 times 6x equals to 30x plus 5 times 8 is 40. This equals to 4 times 3LA is 12LA, and plus 4 times 10 is 40. So here we have 40 on both sides of the equation, so 40 will get cancelled, and we left only with 30x. This equals to 12LA. Here we divided this equation by 12 and finally found out that LA equals to 30x over 12. 30x over 12 is 2.5x. So in conclusion, found out that the length of line segment LA is 2.5x. Here, the length of this line segment LA is 2.5x. Then I copied this quadrilateral with its circle that is described inside it in a new page, then we analyze this quadrilateral ALBT. This is quadrilateral ALBT that I copied from the original drawing. Here we implemented rule 2. If we focus on the common standpoint point A, for the common standpoint point A, we have two tangents to this circle, tangent AK and tangent AN. According to rule 2, they are equal to each other. That is to say, AK equals to AN, or AN equals to AK. It again, the common standpoint A, AN equals to AK. So if we define the length of AN as A, then the length of AK must be also equal to A because they are equal to each other. So in conclusion, found out that AN equals to AK equals to A. Then we focus on the common standpoint point B. From the common standpoint point B, we have two tangents to this circle, tangent BN and tangent BG. And according to rule 2, they are equal to each other. Here, in the common standpoint point B, tangent BN equals to tangent BG. So if we define the length of tangent BN as B, then the length of tangent BG must be also equal to B because they are equal to each other. So in conclusion, found out that BN equals to BG equals to B. Then we focus on the common standpoint point T. From the common standpoint point T, we have two tangents to this circle, tangent TG and tangent TH. And according to rule 2, they are equal to each other. That is to say, TG equals to TH. Here, TH equals to TG. So if we define the length of TH as C, then the length of TG must be also equal to C because they are equal to each other. So in conclusion, found out that TH equals to TG equals to C. And finally, we focus on the common standpoint point L. From the common standpoint point L, we have two tangents to this circle, tangent LK and tangent LH. And according to rule 2, they are equal to each other. That is to say, LK equals to LH. Here, LK equals to LH. So if we define the length of LH as D, then the length of tangent LK must be also equal to D because they are equal to each other. So in conclusion, we found out that LK equals to LH equals to D. Then, according to the same rule, rule 2. Then, we added side AL to side BT. In this quadrilateral ALBT. So it is AL plus BT. What is the length of AL plus BT? From the drawing, it is very easy to see that AL equals to AL plus BT in total equals to A plus B plus C plus D. Again, AL plus BT equals in total to A plus B plus C plus D. Repeat again, AL plus BT in total equals to A plus B plus C plus D. Then we added side AB to side LT. So AB is A plus B and LT is C plus D. So in total AB plus LT equals to A plus B plus C plus D. Again, AB plus LT equals to A plus B plus C plus D. So those two expressions, they are both equal to A plus B plus C plus D, therefore they are equal to each other. That is to say, AL plus BT equals to AB plus LT. Again, AL plus BT equals to AB plus LT. What is the length of AL? AL equals to 2.5x. So we substitute AL by 2.5x plus BT. Here, BT equals to x plus x, that is 2x. So BT equals to 2x. So we substitute BT by 2x. And it is equal to AB. AB is 2, so we substitute AB by 2 plus LT. LT equals to 1.5x plus 2. 2 plus 1.5x. So we substitute LT by 2 plus 1.5x. Repeat again, we substitute LT by 2 plus 1.5x. So in conclusion, found out that 2.5x plus 2x equals to 2 plus 2 plus 1.5x. 2.5x plus 2x is 4.5x. 2 plus 2 is 4. So in total, in this side of the equation, we have 4 plus 1.5x. So in conclusion, found out that 4.5x equals to 4 plus 1.5x. Here we subtracted 1.5x from this equation, and finally found out that 4.5x minus 1.5x is 3x. So 3x equals to 4. 3x equals to 4. We divided this equation by 3, and finally found out that x equals to 4 over 3 units in its length. Here, the radius x of this circle equals to 4 over 3 units in its length. Now the mission is to find out the area of this circle. Again, the radius of this circle x equals to 4 over 3 units in its length. The area of any circle is pi times the radius of the circle squared. The radius of our circle is x, therefore pi times the radius squared is pi times x squared. And we already found out that x equals to 4 over 3. If x equals to 4 over 3, it means that x squared equals to 4 over 3 squared. So in conclusion, we found out that the area of our circle, the area that we are looking for, equals to pi times 4 over 3 squared. Pi times 4 over 3 squared equals to, actually 4 over 3 squared equals to 4 squared, that is 16, over 3 squared, that is 9. So in conclusion, we found out that the area of our circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. So repeat again, the area of this circle equals to either 16 pi over 9 square units, or in terms of numbers, it is equal to 5.585 square units. Okay, thank you very much.